All right. So let's get started. So first of all, I'd like to welcome you to the very first ever workshop through the Math Lab. My name is Jacob Stewart. I've been with the Math Lab since fall of 2019, but I myself have been 3D printing since about the summer of 2018. And so the whole point of this presentation and workshop is more so just to get students familiar with the general process of 3D printing, not so much how to do it here or with 3D printers you can buy, but more so just the general process of working through all the steps, okay? So first of all, I just want to find out some more about the audience. So, have you ever 3D printed before? So we have a yes and a no. Interesting. And then, are you both familiar with it? Semi. Okay, not a problem. See, that's the whole point of this thing. So, first, let's define what 3D printing is. And I'm going to apologize right now. This will get technical with it. But it's an additive 3D manufacturing process that is typically conducted through the placement of layers of material, whereas most manufacturing methods are actually subtractive. You start with a block of metal or plastic or whatever, and you remove material from it. This works the other way around, all right? And now we're going to get to the anatomy of a 3D printer. So first, So this will be the build plate. And essentially, that is the surface that whatever's being printed will be printed on. And it ultimately is what is meant to hold the part in place. If whatever you're printing doesn't stick to the build plate, then it's not going to turn out the way you want it to be. Then we also have the extruder, and this part of the machine is responsible for getting hot. And by hot, I'm talking upwards of 200 degrees Celsius or hotter depending on the material. But its whole job is meant to heat up the plastic and extrude it through a nozzle to precisely place it per each layer. And then now we're going to get into more or less the two different types of FDM 3D printers, which those are the ones that you typically see where the spool of filaments and how they work. So you have direct drive and Bowden tube. Direct drive is exactly as it sounds. There's a motor right above the extruder that is directly feeding the filament into the extruder itself. Now, there's also a Bowden tube. And the difference between the two is simply one has a tube and the other one doesn't. Bowden tube designs tend to be a lot nicer because they have less weight over the extruder, so they can typically print faster because they're not having to worry about jerking a lot of mass around, which causes a lot of inconsistencies in parts. Direct drive tend to have more weight about the extruder, so they have to print slower to get the same level of quality. But both of them are easily you can use them both just as fine. And then there's just the source for the image itself. So now we're going to move into some of the uses of 3D printing. So big one is prototyping. 3D printing is never meant to be a mass production method, but the ability to quickly modify, remake, and test a part to see if there's any more modifications makes 3D printing fairly ideal for the process of prototyping. You can also do it as a hobby. There are plenty of people that actually 3D print, and they 3D print their own accessories for cosplays. People have figured out how to 3D print so that way they have mesh fabric, and they can 3D print the scales onto it. It takes a little bit of figuring out how to do it, but it can be done. And then you can even do DIY home fixes. People have actually noticed things break around their house, and they're like, instead of buying it, I'll just design it and print it myself. You know, if you have the ability to do so, it can save you money because a spool of filament typically costs about 30 bucks. It's just a matter of how much time do you want to put into it. And there are some countless others, but these are just a few of the very easy ones that come to mind. So now we got to get into the limitations because every process has its own limitations. One of them being printer specific, meaning that your printer, whatever printer you use, has limitations and you can only print parts that are within those limitations. Case in point, a lot of printers that use filament typically come with 0.4 millimeter nozzles, which means you're limited on the detail. Yes, you can get smaller nozzles, but then you're also increasing the amount of time it takes to print the object. So then, again, with those printer-specific limitations, there's going to be print quality. There'll be resolution, which comes down to the detail, level of detail that's involved. The materials, because some printers can only get up to a certain temperature, and other materials require temperatures above that. Case in point, nylon. You can 3D print with nylon, but the printer needs to be able to exceed 300 degrees Celsius at the extruder to make that work. Whereas a lot of 3D printers can easily handle PLA, which prints at a much lower temperature of about 200, 210 degrees Celsius. And the temperatures vary within. There's also time requirements. So as I said, it's an additive process. It prints it by layer. It will take time. It's not as simple as just printing on a sheet of paper. It will take a lot of time, depending on how many layers and everything else. And then printability. And that comes more into whenever you're designing something for 3D printing, you try to keep details such as minimizing supports, because you're trying to do whatever you can to minimize any wasted material, and by eliminating supports, you can actually reduce the print time of the project, of the part itself. So now we're going to move into the general process, and no matter what 3D printer you use, this process is generally the same. So first, you have to obtain an STL file. That file format is simply just like a CAD. You can make it in any sort of CAD software, but we'll get into that. Then we have to convert that STL file into Gcode. And the Gcode is specifically what talks to the printer to let it know where it needs to move the extruder. And so therefore, you kind of need it just to print the object. And then you need to get the Gcode into the printer. And each printer will have its own way of doing it. The printers that we use in the math lab are different than ones that you would buy. But still, you're going to want to get that Gcode into the printer before you move on. So now we're going to look into obtaining an STL. And there's many ways you can do this. You can do it through CAD software, such as Tinkercad, which is a browser-based free software you can use, but it's very basic. Drag, drop items. You know, you get very little customizability. You can still do things with it. It is free, but you're limited by your capabilities. There's SolidWorks, if you know how to use it. You might recognize NX. NX can also do this. And then there's many other software. It's just that I don't want to go into listing them all, because there's a variety of options, and they vary from platform to platform. But there's many ways you can do it. You can use Mathematica. Takes a little bit of fun coding that you learn in Calc 3, but you can do it. And Thingiverse, which frankly is my go-to. If it's something that I'm just looking for something fun to print, or if I don't feel like I want to take the time to design it, I just go look into Thingiverse, which is a free online repository where you can download STL files from there. A little bit of warning though, it is stated in Thingiverse's terms of use, you are not allowed to make money off of anything you download off of it. Just because people are putting those up for free, and you know, they're not expecting any sort of payment. They're not getting paid for whatever they're putting up there, but it is available. So now we're going to get into Mathematica, because Thingiverse is an easy website you can just go to and see. And this video was actually made specifically, in part, it kind of goes along with this, but this video actually predates this presentation, but it still actually shows you how to use Mathematica to make an STL file.
The way it works is you provide a list of functions for x, y, and z, and you provide the bounds. However, if I run the cell as it currently is, we get a shape where the walls are very thin, and in fact they're technically infinitely thin because it's a series of points. This cannot be used to 3D print because it's a sheet of infinitely small thickness, which is a problem. To fix that, you have to include a plot theme thick surface. What that does is it provides thicker walls, so that way your shape actually has dimension to it. So if we run the cell again, we can notice now that we've got thicker walls, and then for this shape can be 3D printed. An important note is that even though I'm going to be showing you these commands, this is not a tutorial on how to use these commands. I am merely just showing you examples of commands that can be used in Mathematica to produce these 3D shapes.
Now I'm just going to stop it there because in reality that covers most of it. There is some code that is shown later on in this video, which can be found through YouTube. You just got to go to the Math Labs YouTube channel and you can find this exact video, where more so towards the end of the Mathematica portion, it shows you how you would go on to export the file from Mathematica. But as you can see, it's just using a simple parametric plot 3D command, and you can put in a series of expressions, and you can end up creating shapes. Granted, getting dimensional, like actually dimensioning stuff like you would in CAD software is a little bit more difficult in Mathematica. If you want to, you can take the time, but this is more of like if there's a 3D shape that you find cool in math and you want to print it off, this might be the better route to go. Whereas CAD software is probably your better bet if you actually are looking to make dimensioned objects. Make sense so far?
The way it works.
Ignore that. Okay. So now we're going to move on to converting the STL files to Gcode. And this portion there's a little bit that's involved with it. So first, we got to use a slicer. And all that is just a simple piece of software. A lot of them are free, where it actually will import the STL files, show you what it looks like on the build plate, and then based on the profile that is set inside of the software, it will then convert the STL to Gcode that is compatible with your printer. Now, as I just said, it basically turns the STL files into XYZ coordinates if that printer is set up for XYZ. There are other styles of 3D printers, but again, you're setting up the slicer so that way it is compatible with the printer that you're using. So some of the things that it will tell or include in Gcode are what temperature it's supposed to set the nozzle to. If it has a heated bed, it'll also tell the printer what the temperature of the heated bed is supposed to be. It'll then also tell it the rate at which it's to move, how fast it's supposed to have a cooling fan, and there's other settings that get set. But I want to focus on that the rate of cooling. That's more of a specific for printers. The reason why I say that is the printers in the Math Lab don't actually have a cooling fan that is designed and intended to cool the filament as it's being printed. So you kind of got to watch what some settings are. It's not going to be a big deal, but being able to cool down the material as it's being printed can be proved beneficial, especially when trying to keep stuff within tight tolerances. So now let's get into some of those slicing specifics. So as I said, it's going to be a printer-specific profile. In fact, a lot of software and slicer softwares, when you go to set it up for the first time, it asks you, what printer are you using? And that's just for the purpose of you need to have a printer set up so that way it kind of knows what dimensions, what objects are allowed in the print volume. But a lot of them have these basic functions. So you can generally scale an object inside of them. You can rotate them, center them, you can copy them. And then there are just different types. So there's Cura or Ultimaker Cura. There's Prusa Slicer, Repeteer Host, and those are the three big ones. I'm just going to go back. So those basic functions of scale, rotate, center, and copy, those just allow for you to manipulate the object on the build plate. So what some people have done is they might have something really small, but they need a lot of them. So they'll copy it and then actually have it set up an arrangement for them on the build plate so they can kind of maximize how much they're putting on the build plate. Whereas these different slicers, they all do the same thing. It's just a matter of personal preference. So now we'll kind of just get into what Cura would look like, at least from an interface standpoint. This is relatively basic, but as you can see on the left side of the image, you have a folder that allows for you to open up and actually import any STL files. And below that, they're shaded out, but there are the different options that I had explicitly stated. Cura also gives you the benefit of doing per model settings, but I have not messed with those very much. And generally, you don't need to. Now, on the right side where it's got all these settings, you can see that it's set up for an Ultimaker 3. And then these are relatively basic. And what's kind of unique about this one is that, in fact, it's actually a dual extruder. And that's just shown by the fact that they have extruder 1 and extruder 2. So that gets into more complex 3D printing, but this is a relatively basic. There isn't a more advanced version of the settings, but in general reality, you only need to focus on more so infill, whether you need supports, and what type of build plate adhesion you need. You don't need much more than that. Now we'll move on to Prusa Slicer. If you ever get into 3D printing, you'll likely hear of Prusa 3D printers. They are a really expensive but really good printer. And this is a slicer that you can get to use with them. And you can even use it with other non-Prusa 3D printers. This one is roughly the same. You choose print settings. This one allows for you to choose filament settings, which you can set up in Cura as well. And then you even choose the printer and choose supports. If you want to get into more advanced settings on this one, it's a different process. But you can still do the same things of copying, scaling, moving around, centering. Basically everything you can do in Cura, you can do in this. And what's really nice about Cura, Prusa, and even Repeteer Host is that once the object's been sliced, you can preview it layer by layer. And so what's kind of cool is that you can actually see what's infill, what's support, what's wall, what's shell. You can see what makes up all the different parts. And then we'll just show Repeteer Host. So I'll admit, this is an old interface. They have since upgraded. They're on like version 2.23 or something like that. So this is more of an older interface, but it's still the same thing of you can bring objects in, you can scale them, copy them, center them, and everything. But what I really like about Repeteer Host is that if you're able to connect the computer to the printer directly, this software can actually be set up to connect with it. So that way, instead of manually messing around with the printer to get it to do what you want, you can have this software do that for you. So you can tell it, set the extruder to this temperature. You can tell it to home just the X, Y axes, or you can tell it to home all of them, or you can tell it to just home the Z. You can choose to extrude material. If you're looking to change out filament, you can do that all through here without ever having to fiddle with it on the printer, which sometimes can be easier. It's really up to you. But that's just one of the reasons why I like Repeteer Host. But all slicers are really good options for you. And in fact, most printers, if you buy them, they'll actually come with a version of Cura, a Repeteer Host, or Prusa Slicer with them. And it's just a matter of choosing whatever you prefer. And so now we're actually going to go into the Gcode to physical object, which I like to think of it as the easiest step. Because assuming everything goes properly, you tell the printer what it needs to print, and you just watch the printer. Again, that's ideal. So I like to think of it as akin to watching paint dry. That being said, there are some important things to watch for. So you want to make sure that the first few layers of the print are actually sticking to the build plate. If they are not, again, you're going to have issues. You don't want whatever's being printed to break free from the build plate until it's done. And then another thing you want to check, and this is very common, especially with PLA as it gets older, is that sometimes it'll be printing just fine, but then the filament will break, and the printer doesn't know that it broke. It just keeps trying to feed it through, but it might not ever start refilling. And this is, I've seen it more common with Bowden tube printers, where the filament has broken inside the Bowden tube, and the printer has just kept going on, And so what you kind of notice is, a few hours into the print, it may have started on the build plate, but now it's maybe an inch or two above the build plate, and it's not printing anything. So it's a thing you got to watch for. And then another thing too is you want to watch how much filament's on the spool, because sometimes you might be thinking, oh, there's enough filament on the spool, and then you could be 5 hours into a print, 7 hours into a print, and then you start realizing, oh no, there isn't enough filament. So then you kind of got to figure out what to do there. However, granted, most of the time you kind of want to look at it and go, is there enough on there? Do I think I can get by? If you don't think you can, it's probably just better off to go to a new spool of filament to get that worked out. And then once it's done, you just peel it off the build plate. Now, that might be honestly one of the harder parts to do in this whole thing, because it could be really stuck to the build plate, but there's nothing wrong with that. It just might take a little patience, a little bit of time and practice, and you can eventually just peel it off the build plate. Now, this actually occurred to one of the printers in the math lab where it went unsupervised. That's always a pain. It can be cleaned up. It has been cleaned off. But this is one of the reasons why you want to watch it, is because that can happen. And now, 1, you've wasted material. 2, you've wasted time. And you got to waste even more time now to clean it off. Like I said, that has been since cleaned up. It's not generally hard to clean up. You just got to be careful, because there's components that are going to the heating element and the thermistor, which is like a temperature gauge. It's telling the printer exactly what the heat block is at for temperature, and you got to make sure that you don't cut wires. But it's just something you got to be very careful of. But like I said, that's the reason why we don't leave 3D printers unsupervised. So now there's other variations of 3D printing, and these are just more like good to know, but they're just, at least they're kind of cool in my opinion. So there's SLA printing, which is generally called resin 3D printing. Those printers operate differently, but where FDM printers typically have a hard time getting small resolutions, resin 3D printers are typically known to print to the level of microns fairly consistently, no matter which one you get. So you can get much better detail on them, and it can even take about maybe the same amount of time, sometimes longer, but you can make figurines with resin 3D printing. And then if you're just curious, that's just stereolithography. Essentially what there is there's like an LCD screen that is below the bottom of the vat of resin, and the build plate just simply goes in the resin, and the LCD screen will allow the UV light through in specific areas, which cures the resin in those areas. Then the build plate just simply moves up, allows resin to fill in, and it repeats the process layer by layer. So it prints an entire layer at a time, rather than watching it do a layer. It will do a layer each time. There's metal 3D printers, and these ones you'll more see in commercial aspects. They'll be used in terms of prototyping metal components that are needed to be out there, which they typically will use metal powder and lasers, and that's a different idea of 3D printing. The idea with that aspect is that they put a layer of powder, the laser heats up and melts the metal in the specific spots that it needs to be, and then the machine just repeats the process. And what's cool about it is the powder that doesn't get melted is used to support the next layer. So they can end up having really good detail, and the object's made of metal. Granted, they do take a while, and you then have to spend time cleaning out anything that's left in the part. But, it's used in commercial aspects. There are concrete 3D printers, and the ones I've seen have been used to make houses, where it would 3D print the walls. And you could even 3D print like small roofs and stuff like that as well. Do they look the best? No, but it's another aspect of being able to use 3D printing. And then even hobbyists have made some modifications. I belong to 2 or 3 Reddit subreddits that deal with 3D printing. And in one of them, I saw a video specifically. Someone had made a 3D printer that used clay. And I mean, it was crazy to watch, but it was also cool because then they're getting away with it. Instead of having to shape the clay into like cups and bowls and stuff like that, they can just 3D print it. It just takes a little bit. So now I guess I just open the floor up to you guys. Are there any questions that you have? Okay. So the first one was how much do they cost, right? So so the cost of the printer depends on several aspects. One, what are you looking to do? Are you looking to get a kit, or are you looking to get one that is ready to go right out of the box? I know I've kind of dabbled in both of those a little bit. My first 3D printer was an ANET A8. That is specific. It was specifically a kit because I specifically wanted to build it myself. That cost me, with shipping included, about $150. The second one I got, I had to attach basically the anything dealing with basically the Z-axis and the gantry that moves in the X-axis. But that one was like $250. But what was kind of nice about the more expensive of the two was it came with a filament runout sensor. So then the printer would stop a print if it actually sensed that it ran out of filament. And it also came with an on-off switch. The ANET A8's only way of turning on and off, unless you modify the cable going to the power supply, is to unplug it and plug it into the wall, which isn't ideal. Now, prices, as 3D printing becomes more popular, prices actually have been dropping. So that kind of helps in terms of getting a 3D printer that way. In terms of materials, typically you can get a 1 kilogram spool of PLA, which is the easiest material to start 3D printing with, for about $30, as I said. And it's not like 1 kilogram spool is going to last a short while. You can do some pretty big, I've done 18-hour prints off of 1 spool of filament before. So in terms of that regard, you know, the costs are getting better, especially now since materials are becoming more diverse. I know Jason wants to get into having a 3D printer that uses water-soluble filament. And the idea behind that would be you have a printer that is able to use 2 materials at the same time, where the water-soluble filament is actually meant to be support material, so that way you can just dissolve it. Instead of having to peel it away from the part, you can just set the part in water and it'll dissolve. Now, in terms of the whole AI thing, that one's probably a bit farther yet, because that's not where a lot of things are focused. A lot of it is turning into more of the hobbyist thing of, you know, let's actually push this thing to the limit. And a lot of people do. When I started getting into it, I reached out, or I watched videos from Maker's Muse and 3D Printing Nerd, both of which have made their YouTube channels on 3D printing, so they've done a lot with it. They've reviewed 3D printers, they've worked with filaments, and they've done a bunch of crazy things on their channel. So, you know, you just gotta, if more so, just like any topic and hobby you want to get into, you really just gotta do some simple research into, what's good about this printer, what do I not like about it, and stuff like that. Any other? And I will say, Cura, on that note, Cura's done something similar. So in part of the advanced settings in Cura, you can do variable layer settings. And more so what I've seen the application in that would be for test prints. So when you get a new filament, if you're not sure what temperature on your printer is the sweet zone for it, there are prints that people have made where you can set it so that way after so many layers it changes print temp to go to higher, or it starts high and works low, which way it ever goes. And then you can actually, once it's done, you can say, okay, well at 180, sure it looks nice, but it's really brittle because there's not much layer adhesion because the material wasn't hot enough. At 220, it was too hot, and it all just kind of muddled together. But, right around 200 was just fine. So it turns into ways of, you kind of got to work it out per material and your printer. But if you take the time to do that, you can get some really good prints. There's even things people have made like trebuchets and catapults that are print in place. So it prints the entire thing together, and then you simply bend and fold a few things, and you now have a catapult. Doesn't do a whole lot, but it's something, cool that you can make. Like I said, 3D printing is more so turning into more of the hobbyist profession. But for those that like to prototype and stuff like that and do their own design work at home, 3D printing tends to be a very good way of doing that. Any other questions? Well, so you would buy the spools of PLA. And what's unique about PLA is it's actually a plastic derived from corn. There'd have to be more research into that, because it's more or less they were using byproducts of corn production, and they were able to pull out the polymers from there to make the actual plastic itself. Like I said, there's nylon, there's PETG, which is a more complicated material, but what I like about it, and actually the Math Lab does have some, is that it prints like PLA, but it has the strength of ABS. When 3D printing just first started becoming a thing, ABS was the only plastic you could use. The trick with ABS, though, is that unless you have a heated enclosure, it warps very easily, because it goes from at least 250, 260, and then it's cooling down quite far. And so in that process, it warps unless you have a heated enclosure. Where PETG makes it nice is it prints at those higher temperatures, but because of the polymer chains in it, it doesn't constrict and warp that much, so it prints more like PLA. So, yeah, PLA is the now really go-to material to start with. Yep, so, yep. Yeah. Perfect example, ABS will produce fumes. Trust me, I know. I have ABS, it's not fun to print with, and it does make fumes. The rubbery material that Jason was talking about is called TPU. Essentially, it's a cool material, but it can also be a little bit difficult to print with. The reason being is it's more flexible. It's a more flexible filament. So that Bowden tube design, if your Bowden tube does not have a tight enough tolerance on the inside diameter, it can end up bending inside of there and not wanting to feed properly. But what's kind of cool about TPU, and actually the Math Lab does have an example of it, it's a pink dinosaur, is that once it's printed, it's not a rigid object. It actually is somewhat flexible. So there are other materials out there. It's just that PLA is typically the go-to for just getting into it. As you become more experienced, then you can expand into other materials. And there are some other aspects, like the materials that you use can wear down the nozzle. We didn't cover that because that's more of a per material basis. And if you just use straight old PLA, you're not really going to worry about that. It'll take a lot of time for it to wear out the nozzle. But I mean, there are filaments that glow in the dark. There are nozzles that have carbon fiber in them. It's just the material you use, depending on how abrasive it is, wears out the nozzle faster or slower. So generally you want to stick with just PLA. Yeah. You're going to find that's a more limited. Some people do it, but the thing is you need to keep a rather consistent filament diameter size. So making your own filament's kind of harder to do, and it requires a whole nother machine. And actually, it's funny that you bring that up because 3D Printing Nerd actually has tested machines that are designed to take scrap PLA, and even you can buy the PLA pellets, so that way you can make your own. And do they work? Yes. Is it really that easy to just use at home? Not quite. If anything, that's where it's more going to start transitioning over. There are other machines like there's a machine made by Mosaic that can take 4 different color filaments, and you can actually have a colored 3D printed object. But that is more complicated because you have 4 different filaments that I would surmise have to be roughly the same melting temp because they're all going through one nozzle. Because the way the machine works is it actually splices the specific lengths of each filament together to be fed into the printer. So if you have PLAs, like if all 4 have PLAs, you should be fine. They all should melt roughly at the same temperature. But what you're not going to want to do is you're not going to want to mix a PLA with an ABS with a nylon because that transition's not going to be smooth. For the fact is your printer nozzle is going to have to go through a variety of temperature changes just to actually achieve that. But the making your own PLA, that's kind of a thing of, it's out there, you can find it, but it's not really cheap. The one machine that I saw that could do it at home, I think was like $500 to $700, maybe more. So it's significantly more expensive than the 3D printers you can buy to just get into it. And then $30 for a spool of PLA is not, you can spend probably less than $200 and get the printer and filament versus paying over $500 for a machine that makes your own. So that's one of the challenges of PLA right now and other filaments is you have to have a specific diameter so that way it can easily feed itself and feed the material into the printer itself. Does that make sense? Yeah. Yeah, let me just, yeah. And then this is just a feedback form. So if you want to do that, so. Okay.